All right, in this video, we are going to talk about some rules of probability. So the first one that we are going to talk about is the general addition rule. So remember back in the previous section, we talked about the OR event. And so this rule here, the general addition rule, tells you how to calculate the probability of the event A or B if you know the probability of event A, the probability of event B, and the probability of A and B occurring. Okay, so this rule works as long as you know these three things. It's like the name implies, a general rule. This will work every time, as long as you know these values here for calculating the event of A or B. So this part here seems natural, the sum of the probabilities, the probability of A plus the probability of B. What a lot of people don't get is why you have to subtract off this probability of the event A and B. And that is because, right, in a sense, when you do this, when you add the probability of A and the probability of B, if there's any overlap between A and B, you're essentially counting that overlap twice. Okay, so let me pull up this so I can draw a picture for you. Oops. So you can think of calculating probabilities as areas in a sense. And so let's say you had an event A and some region in here, and the area of enclosed in this little circle or figure here is the probability of A. And then if you have another event B like this, and there's some overlap, right? This part in here, if you take the area of A, the area of this region right here, and then the area of this region right here, and add them together, what you've done essentially is count this overlapping part here twice, right? Once in the area of A and once in the area of B. So what you would have to do is to subtract out, right, the area of this little intersection one time. So you're only counting it once. Okay, so that's a little bit like how this rule works right here. If you add the probability of A, that tells you the probability that event A occurs. This tells you that the probability of event B occurs, but those things that are inside both A and B, right, are going to get counted twice when you do that. So what you need to do is to subtract out the area that's common to both. And if you remember back, that is just the event A and B, right? That is the event that both A and B occur. So those are the elements of your sample space that are in both A and in B. So that's the idea behind the general addition rule. Okay. Okay, so let's jump right into an example. This example is from our book 4.96 about naturalization. It says the U.S. Bureau of Citizenship and Immigration Services collects and reports information about naturalized persons in statistical yearbook. Following is an age distribution for persons naturalized during 1 year. So over here are their ages, right, of the people that became U.S. citizens, and here are how many people in that age group became citizens. Okay, and the table continues over here with ages and then frequencies as well. Okay. So it says if one of the naturalized persons is selected at random, find the probability that the age of the person is between 30 and 64 inclusive, or at least 50. All right, so I'm going to take a second. I'm going to write that down. So we want the probability that the person is between 30 and 64. Or at least 50. All right, so that's going to look like this. Okay. So normally what we have been doing in the past is just writing a single letter for an event, like A or B or whatever. But here I'm just going to write something that's a little bit longer, right? So that way it's kind of a little bit quicker. We don't have to write let A be the event that the person selected is between 30 and 64, or B be the event that the person is at least 50, right? And you can kind of remember what it was. Sometimes when you're working that problem, you have to like refer back and see, okay, what it is. So these are just event names that are a little bit longer than what we normally write. So like, for instance, this would be kind of like serving the role of event A, right? And this would be kind of serving the role of event B, the event that the person selected is at least 50, okay? All right, so I want to calculate the probability of that event. And so what I'm going to do is go back to the chart here, right? And look at the chart. Actually, before I do that, I am going to go back to this formula right here. So we're going to use this general addition rule, okay? And so I'm going to write that out. So that would be the probability of A or B, right? Would be the probability that the person is between 30 and 64 inclusive. That means including that number 30 and the number 64, right? And then the general addition rule says that would be plus the probability that they're at least 50 okay, and then minus the probability that they're between 30 and 64. All right, I gotta rewrite that. This doesn't look good. And at least 50. Okay. So that would be applying this general multiplication rule, right, to this particular problem. Okay, and then what we would do is to go and calculate the probability of each of these events. So first, let's do the probability that the person selected is between 30 and 64 inclusive. All right, so we need to go to where our frequency distribution is, and I want to be able to draw on this, so let me just pull it up. Okay, so we want between 30 and 64 inclusive. So that would include all these people here, right? All the way down to these people here, right? 64, okay? So to calculate that probability, what we would have to do is to add all of these numbers up, okay? 64,735, 69,844, and so on and so forth. All right, so we would add all these numbers up. I already did that just to save a little time. Okay, and so that would be this number right here, between 64,735 all the way up to 18,767. So what I get is 312,108 as the top number. All right, so 312,108. So going back over here, right, that would be the top number on this probability right here. All right, so next thing that I would need to do is to get the total number of people in my sample space. And so in order to do that, what I would do is to add up all of the numbers. That would be next, right? So starting here, 5,958, add all of these numbers up, right? And again, just to speed things up a little bit, I've already done that up here, right? So you can see I've added all those numbers up. And that comes out to be 463,200. Okay, so that is going to be this number that goes on the bottom, 463,200. So let me just double check those. 3112,108, that looks good. 463,200, that looks good as well. All right, so there's our probability. All right, next up is we want to get the probability that they are at least 50. Okay, so the bottom number is going to be the same, right? That's going to be the number in our sample space. So 463,200 on the bottom. And then now we want the probability of at least 50, right? So let's erase this. So at least 50. So that would be right here, right? And that would include all of these people right here, right? And so we would have to add up these numbers, 32,574, right, all the way down to 9,872. So I have that one done already. Right here, 32,574, 9,872. That gives us 112,275, right on that. All right, so that number would go on top right here. All right, next up is the we would need the probability that both of those events happen, right? And so that would be the probability that the person selected is both between 30 and 64 and also at least 50. All right, so the bottom number is going to be the same again. The top number, though, right, we're going to have to go figure that out. So between 30 and 64. All right, so between 30 and 64 would include all these people, right, all the way down to here. And then at least 50, right, would include all these people here, right? And so what we want are the people that are in both, right? So that would be this group here. All right, because they were in both the first event and the second event. So that's what they have in common. So we would add these numbers up. I didn't do these numbers yet, so we will need to do that. Let me just drag this over and then do it off screen because it's easier. Actually, if I move that back here, we should be able to see it. Okay. All right, so 32,574 plus 25,534 plus 1,877. And that comes out to be 76,875. All right, so 76,875. All right, so that's not what I wanted to do. Neither was that. All right, let's see if I can pull this up again without destroying anything else. Okay, I think we're good. I really did not want to do what I just did, but that's fine. We'll figure it out. All right, and so just give me a second here. And I can get that back up there. 4-3. All right, there we go. All right, we were right here. Okay, so Now what we want to do is to calculate this probability. All right, and so all of these fractions have the same denominator, right? So we can combine those fractions in the numerator, or combine the numerators and keep it over the same denominator, right? So there we go. And we would have on the bottom 4, 6, 3, 2, 0, right? And then we will need to, all right, so let me see if I can do this without breaking everything again. All right, so here I've got 312, 108 plus 112,275, just adding the numerators up, and then subtract 76,875, and I get 347,508 on the top. On the bottom, I would get 463,200 right on the bottom. Just double check that. Looks okay. All right, and then let's go ahead and just get a decimal approximation here. So 347,508 divided by 463,200. All right, and I get 0.07502, 3 decimal places. Right. So that's the probability of this event here. So about 75% of the people that year are between 30 and 64, or at least 50. So the probability, right, if you picked one at random, would be that they would fall into this category would be 0.75. Okay. Okay. And again, that minus part, right, we are subtracting out the numbers that are in both of these categories here. Okay. So that's the reason why we're subtracting off this probability. All right, so that's the general multiplication, our general addition rule. You can get around using the general addition rule, right? In this particular problem, if you are careful not to add these numbers twice, right? If you just do those one time. So I'm not going to show you how to do that, but you can. But there are just some certain problems where you will not be able to do that at all. So let's take a look at one of those. All right, so I'm going to clear this off, and we will take a look at another example. All right, and that's example 4.98. Okay. All right, it says gender and divorce. It says, according to America's Families and Living Arrangements published by the U.S. Census Bureau, 51.5% of U.S. adults are female, 10.4% of U.S. adults are divorced, and 6% of U.S. adults are divorced females. What is the probability that a randomly selected person is female or divorced? Okay. All right, so the big difference between this problem, right, and the previous problem is in the previous problem, right, we were able to actually see the frequency distributions. They told us, right? And we could count those up and, use those numbers however we want to calculate our probabilities. Here, we do not have that. All they tell us is these percentages, right? And so, but these percentages are actually probabilities as well, okay? All right, so going through this, what they want us to know, or what they want us to find out is what is the probability that a person we randomly selected is female or divorced. So I'm going to write that as a probability of F, right, for female, or D for divorced. So I'm going to write that out like so, okay? All right, and we want to calculate the OR, right, of these two events, F or D, and so that is the generalized addition rule. So that would be the probability of F plus the probability of D minus the probability of F and D. All right, so that's using the general addition rule. Okay, and then what we'll need to do is to go back through the problem and see if we can figure out what's the probability of F, what's the probability of D, and what's the probability of F and D. Okay, so reading back through the problem, it says 51.5% of U.S. adults are female. Okay, so what they are telling us is that the probability of F, if you randomly select somebody out of the population, it is 51.5. I'm going to write that as 0.515 as a decimal. Okay. So sometimes you can report these probabilities as fractions, right? Because remember, they're all numbers from 0 to 1, so you can report them as fractions. You can report them as decimals as well. We've seen that. You can also report them as percentages. Okay. But generally, right, when you are going to do arithmetic on percents, right, you just generally change them to decimals, and then so you don't have to learn extra things about percents, right, and doing the operations. So I generally convert those on over to decimals, and I almost always kind of report these probabilities as fractions or decimals, unless the problem specifically states that they want percentages. So okay, so we know that the probability of female is 0.515. All right, reading through it says 10.4% of U.S. adults are divorced. Okay, so that would be the probability of D. Probability of D is 10.4. So as a decimal, that would be 0.104. 10.4. All right, and now what we're missing is the probability of F and D. So that would be the probability that a person randomly selected is female and divorced. And so it says 6% of U.S. adults are divorced females. So that would be female and divorced, right? So it's 6%. So that would be 0.06 as a decimal. All right, so now we are good to go. All we need to do is to put those numbers in the correct spot over here. Probability of female is 0.515, plus the probability of divorced is 0.104. And the problem here is that somebody can be both female and divorced, right? So when you're doing these probabilities, it counts those people twice. So what we'll need to do is to subtract off one probability over here, right? The probability that the person is both female and divorced as 0.06. Okay. All right, and then what we would do is just do those numbers out, and so we would get 0.515 plus 0.104 minus 0.06, and so we get 0.559 as the probability here. Now, as a percent, that would be 55.9%, but again, I just kind of rather leave it as a decimal. That's what I'm used to when I'm calculating probabilities, or a fraction. Okay, so I just want to again point out how this example is different, right, from the other example. In the other example, right, 4.96, they gave us a frequency distribution, right? So we had to come up with all of the probabilities ourselves, and we did that, right, by adding up all the things in the sample space, right, and then we found the number of observations in our event, and then we divided that to come up with the probability. So again, these are frequencies, counts. How many people? 5,958 people. Okay, So when they give these as frequencies, that's what you're going to have to do, or counts, however you want to, whatever you want to call it, the number of people or the number of observations. So you're going to have to add them all up, right, and divide by the total number in the sample space. And so in problem 4.98, right, they're giving us percentages, right? And another way you can look at these percentages as probabilities. So they are giving us the probabilities. We don't have to calculate those ourselves, okay? And so, but the thing is, we can't, that means in this example, we pretty much have to use the general addition rule. There's no way around it. I didn't show you, right? But in this example, I said, hey, we could, if you're careful about how you count these up, you can actually avoid using the general addition rule, but because they gave us the counts, we could do that, right? But in this problem, because they gave us probabilities disguised as percentages, right, there's no way you can do that. You must use, right, this rule here. There's really no way around it, okay? All right, so that's it for the generalized or the general addition rule.